All right, let's continue or begin, I guess. So, right, last time we finished discussing random variables in general and moved on to discuss or to focus, right, on discrete random variable in particular. And so the one thing, right, about discrete random variable is that we want to know is PMF, right, probability mass function. Namely, that would be the starting point, right, to figure out all the things about the random variable, right? So, of course, there are indirect ways to describe the random variable, or there's scenarios where you won't be able to find the PMF of the random variable very easily, which is a more advanced case. But at least, right, by default, if you don't know the PMF of a discrete random variable, then you don't know it completely. You're missing information about it. And right. And so then the next idea, right, is that you just don't have a random variable, but you can create new random variable, right, from the given random variable, right? So given a random variable, you can create new random variables. And this basically, right, gives rise to infinitely, right, many new random variables from known random variables. And the combination basically, right, can come from the mapping of a single random variable, or right, combining them with arithmetic operations, or right, just basically functions of multiple random variables. And the one thing, right, that would distinguish random variables from events would be things like expectation, variance, and higher moments, because right, basically these are things that have numerical values, right? And exactly, right, that highlight the part, right, that random variables play that random events in general do not. That is, right, random events by themselves don't have numerical values attached to them naturally, right, by default. And so these are like kind of general framework, right, that would apply to any random variables. And then to kind of start working, right, or start having basic models, right, so that we can create more models out of that, we will introduce, right, these well-known models that basically are talked about in any, right, courses in probability. I mean, not in probability, but involving probability, right? In statistics, for example, would routinely reference these random variables or stochastic process. Okay. And so, right, here again, if we have a discrete random variable, then you can create new random variables, right, out of them by just basically mapping them to some other function. And you need to be able to give the mass function of the new random variables to completely describe it. So it all boils down to, right, tables. So PMF table is just a way to visualize, right, or to organize the information. Obviously, if the random variable takes on a lot of values, then the table may or may not be helpful. But for, at least is there as like a visualization tool, starting right with the PMF table of X, right? Then we can create, right, the PMF tables of all other functions of X, right? And so notice, for example, right, the corresponding values, right, between, let's say, X squared and absolute value of X, right, and how the distribution, right, the probabilities are exactly the same for these two, but of course the values are different, right? Here, right, how the values are different, but the distribution are almost the same, right? Again, this is no mystery, right? It really comes from the fact that the new random variables are just functions of the known random variables. So you figured out, right? Everything is figured out from this table. But there will be another, right, implication of this, like these tables down there, right? When we look at expectation and variance, for example, right, the combining random variables, right, it serve in the same way. So if you have So notice right here, we look at two fair dice, right? Two fair dice. So X and Y are independent, right? And the PMF table for each of them, right, is 1/6 each, right? X or Y, right? But then, right, you see that combining random variables, two or more, right, would yield potentially way more values. And so again, right, the table start to become awkward, but at least it shows us, right, the idea of the visualization, right? Especially for example, X times Y here have a total of 36 values, right? And what else? So for example, right, notice the difference, right, and the sum, right, how the distribution looks similar, right, but the values are different. Again, there's no pattern here, okay, but you just figure out from, again, the distribution of the individual random variables and the fact that they're independent. But basically, when you work through this example, and you should, then you see that there is some correspondence, right? And there's a reason why the numbers come out the way they do. And again, right, these will have some meaning when we talk about expectation and variance. But yeah, right. So here, expectation, which is the sort of the concept, right, that is really specifically for random variable, is the weighted average, right? It's the weighted average of the values the random variable can take, right? Okay. And so, for example, right, if it's a roll of fair dice, then it's a sum, right, of 1/6 I 1 to 6, right, which is 1/6 times 7 times 6 over 2, which is 7/2, right? So on average, right, a fair dice, the value is 3.5. Again, right, that means nothing if you don't really say it carefully, because of course, what does that even mean, right? On average, a dice rolls 3.5, right? That statement by itself means nothing, right? It will have meaning via, let's say, the law of large number, which means, right, that basically if you play, right, if you roll the dice 1,000 times, right, and let's say each game you get paid according to the value that the dice comes up, then, right, on average, each game is as if you gain $3.5 per game, right? That's what it is. So if you roll the dice 1,000 times, and on each game, right, each roll you get paid the value of the dice, then it's as if on average, right, you get paid 3.5, right, for these 1,000 games. So that's the meaning of it, okay, through a law of large number. And so when it comes to a function of a random variable, then something special happens, which is that to compute the expectation of a function of random variable, we do not have to go through, right, the PMF of the new random variable. We can use the original PMF, right, of the random variable X, okay? And that's the advantage. And so, for example, here, right, in the example that we just talked about, so here's X, right? Here's X squared, right? The table for X, right? So this should really be, right, 2/5, right? Okay, like that. And so you see, if you calculate it through the law of unconscious statistician, then you would, oh, sorry. Yeah, if you calculate through the law of unconscious statistician, then you would use this table, right? You would use this table and you square all values, right? You square all the values and to get this. On the other hand, right, if you use the definition of the expectation, then you would use this table, right? Because this is the PMF of X squared. All right. And the point is you will get the same value, right? But this approach, right, this approach by definition require you to use this table, right? And figuring out this table actually is a cumbersome business. If the function is complex, or if we have a continuous random variable, then that's an extra step, right? The point here is, right, if you use the law of the unconscious statistician, there's no new computation that you need. You can use the old table, and you just basically, right, plug in the function that you want to calculate. All right. And right, expectation is linear, meaning that, right, you have a combination of random variables. The expectation of that is the linear combination of the expectations. And the point to remember here is, right, any xy would work here. So you do not need them to be independent. And that's a very powerful result, right? So we'll look at this here. But for example, right, if you look at the dice toss, and here we have independence, but again, it's not needed in this particular example, right? If you want to do it by definition, then you really have to use this table, right, and do this times this plus this times this plus this times this, etc. And you'll get the not surprising result that is 7. Why? Because we know that if we take expectation of x plus expectation of y, right, and it's easy to calculate each of this is 7 to begin with. So here, right, again, this table actually, this example would sort of highlight the reason why we want to know the rule better. Because here, right, definitely this table is very, very cumbersome to figure out, right? And if your task is just to find the expectation of the sum, then there's no need to go through this whole procedure, right? Going through a rule is much easier. Okay. Now, so this is where we stopped last time. So let's address, right, this idea, right, with the hat problem, right? So remember, right, the hat problem is where n people, right, throw their hats together and then pick out the hats at random, right? And so you can, right, now that we have the notion of random variable, we can, right, define the random variable x, which is, let's say, the number of people with the right hat. Okay. And what we worked on before was to find probability x equal to 0. Right, with the whole inclusion exclusion formula, right, with the sum, etc. Right, I think it was something like this, right? 1/2 factorial minus 1/3 factorial plus 1/4 factorial, right? So on until, right, you have minus 1 to the n, 1/n factorial, right? And that's only to find probability x equal to 0, right? Well, just for entertainment, try to think how you would find, for example, probability x equals to 1, probably x equals to 2, etc. How easy is that? Or how hard is that, right? But nevertheless, right? And of course, the implication is that to find these numbers out would not be, let's say, a walk in the park, or you wouldn't be able to write down in just say 1 minute. But the point here is, right, somehow we want to get to the expectation of x. Right? So how is that possible? What can we do here? Any suggestion on something we can try to exploit the linearity of expectation? Any suggestion? So the idea here, right, is to split the total as a sum of the individual. So for example, right, because it's a total, we can look at individually, let's say person I, right? So we can focus on the person I and denote, right, some random variable as 1 if that person gets the right hat and 0 if not. Okay. You will see this random variable very soon, and it's called a Bernoulli random variable. Okay. So yet another reason why, right, these well-known random variables are something we should always keep in mind. But from this point of view, it's also referred to as an indicator random variable. What does it indicate? It indicates whether the ith person receives their right hat or not. And the relation, right, between the total and the individual indicator is actually pretty simple. X will be the sum of xi. Okay. Now, if you're not used to, right, seeing this, or this is the first time you see something like this, take some time to try to figure out why this is true. Right. Now, why does this equation hold? Well, it just literally explains how we count, right? Because let's say we go through each person, right? Person 1, person 2, up to person n, right? And for each of them, right, we see if they get the right hat, right? Okay, if this one yes, this one no, let's say the fourth one is yes, etc., right? So in the end, right, you see that you go through each of the person. If they get the right hat, then you increase the count by 1, right? If the hat is if they didn't get the right hat, then you do not increase the count, or you add 0 to the sum, right? I mean, if you take CS 101, you probably have done something like that with a for loop, right? So that's exactly how counting goes, right? You go through each case. If it's correct, you increase the count by 1, the total count by 1, right? If it's not correct, you keep the same count, meaning you increase it by 0. And so that's that. But from the point of view, right, of expectation, this is very appealing, right? Notice, right, we haven't discussed the notion of independence of random variable yet, but we discuss how the action, right, of the persons in the hat problem are not independent. So it should be here, note that xi's are not independent. Okay. So the action, right, of of different people, right, influence each other. Okay. Nevertheless, expectation doesn't care about that as far as the sum goes. In other words, expectation of this is the sum of the individual expectation. Okay. Now, can we figure this out? Well, right now it goes to an individual person, right? And so obviously, right, by definition of random variable, this will be 1, right, times the probability, right, that the ith person gets the right hat. and plus 0, right, times probability no, right, like that. We don't really have to write 0 times something because 0 times something is 0, right? But we just write that there for completeness. So, well, what is this? We talked about this, right? The probability the ith person gets the right hat is 1 over n. So the answer is 1 over n. That means individually, each of these is 1 over n. And so the final answer is 1. Right. So that's the expectation of the number of persons with the right hat in a hat problem. Any question here? So note, right, a very, very important and interesting feature is, right, this does not depend on n. In other words, right, it doesn't matter how many people there are. On average, there's only one person, right, that gets the right hat. Okay. So let's continue the lecture after we look at the problems. All right, so let's take a look at that one. Okay, so A here is not really rigorous, okay? It's just meant for you to think about, right, the problem and just a sort of like gets you thinking and motivate. It doesn't have to really be rigorous in the sense that you should know which one is bigger, right? Because even if you know exactly what X and Y look like, the numbers might be a little bit, right, not that easy to figure out. There's some sense to this, but right. So instead of A, let's just focus on the X and the Y random variable, right? What's the difference between these two? Is there any difference in terms of their support?
I don't think so, no.
Correct, right? They take on the same values. So let us just arrange it, right? 25, 33, 40, and 50, right? So the difference must lie in the probability. So this should be probably little x, right? And little y, the values it can take. Okay, so let's see, right? What would the first entry be for the random variable x? Or for that matter, if you feel y is easier, what would the first entry for the random variable y be?
1/4.
Or which one?
Uh, well, y
Okay,
for all of them would be 1/4.
that's correct. Very good. So then let's focus on x then. What would the PMF for x be?
X over 148 for each of the x's. Like 20 over 40.
148 as the sum of this, right? So yeah, so 25 over the sum, right? Whatever that is. So 40 plus 50 plus 33 plus 22 is 148, you said? Yep. So very good. Exactly. Right. So that is the difference, right, between x and y. Okay, through the language. Any question here? So the expectation, right, would just be calculated out through that table, right? There's nothing interesting, so we won't write down the expression, right? You do it yourself. But just for fun here, right? Which one do you think is larger now that we write down the table?
It would have to be the expectation of x, because then we're gonna have 25 squared over one. We're just dealing with squares. It has to be bigger.
Uh, I'm not convinced because if you want, this is 25 over 100, right? Okay, so, right, I mean, like, so, fine, right? But you know what I mean? Like, I'm not so sure if the square alone will justify it exactly.
If we can't compute it though, it's kind of hard to just like
No,
guess.
I agree. I agree. No, so I'm really going circle, right? I go against what I said before. Of course, there's no reason why, or there's no right. Absolutely right. So I kind of go against what I said before. I agreed completely. So what I'm saying is I'm not convinced about the square argument, but I would kind of focus on the uniform aspect here, right? Basically, when you distribute the weight, right, uniformly among the values, I think it tends to have a minimizing effect. So I think I agree with you, right? I think expectation of x is bigger, but I'm not so sure the x itself have the square have anything to do with it. But because actually you could put all the weights in here, and I think it's still bigger. Meaning that I think this might be again, right? I don't know my optimization very well, but I think this might be the minimum choice as far as expectation is concerned. I'm not so sure, right? But don't take that claim very seriously. But I would harp on the uniform weight more than the other one. All right, that's the only remark I want to make. But of course, right, if we don't make the calculation here, it's not easy. Anytime. Yeah. So yeah, so expectation of so here my explanation was the higher bus size also receives a higher probability. Yeah, I think actually I think this reason is actually good. I mean, it doesn't play on the minimization of y, which might be wrong, but it plays on the fact, right, that basically notice with the way the description is, right? Notice that the bigger the bus, the more the probabilities, right? So you kind of go all in on the bigger bus size. So clearly expectation of x is bigger from that point. And that might be what you were trying to say with the square. Okay, any question? Okay, all right. So let's take a look at two. All right. So here, right, we deal with the random variable to count the total number of heads, right, in a flip of two coins. So obviously it is 0, 1, and 2, right? I mean, A doesn't ask to do that, but right, because you calculate expectation, so you might as well list everything out, right? So I hope, right, the answer is obvious. So for example, right, this is 0.6 times 0.7. This is 0.4 times 0.3, right? This is 2 times, no, it's not 2. It's not symmetric, right? 0.4 times 0.7 plus 0.6 times 0.3. Agree? And then expectation is just multiplied out. Any question? Okay. All right, so this one. All right, so the challenge with this question is actually to interpret what it's asking for, basically, right? So what is the random variable that we are looking at, or is there even a random variable here? What is a random variable, if there's any here, that we have to look at?
I would say the support would be E and not E.
No, no, no. In English, what random variable are we tracking to begin with? We're not even saying what a value is, right? Because you see, if we don't know what we're looking at, then we cannot even discuss its values. What are we tracking here?
The money you can get.
Ish. I think it says right here, right? The profit. The reason why I don't agree with what you say is I think you're referring to revenue, right? Which is related, but not the same, right? Is that okay? So you could also define Y as a revenue, and X and Y are connected, right? But okay, but I think X is what we're looking at, or more directly to demonstrate, for example, right? So first of all, right, to let's just clarify here: is A random? Is A a random variable? No, right? A is a fixed number. Okay. So the question, whatever it is, ultimately requires us what? Expectation of X is 0.1 of A. Correct? Now, if you define Y as a revenue, then what do you need? Expectation of Y. Yeah, it's kind of hard, right? So I think it's the profit that is really easy to look at. I'm not sure about the money. So maybe we can have a way to look at that later because profit and revenue are connected, but is that okay? So it's really profit here. But so now that we look at that, let's look at what values X can take. Right? What value can X take? So here's the thing, right? The question asks for what should it charge? Correct? So actually, that goes to the amount it receives. I think, okay, I think I know what you were saying now. But notice, right, the point here is the amount it charged. This right here, right, also is not random. So when you say that it's a random variable, actually is actually will be confused. Right? We're not charging a random amount, correct? But the profit will be random. Why? Because the profit depends on whether you have to pay out based on the event, right? Based on the accident or not. Does that make sense? It's very easy, right? Think of auto insurance. What they charge you is a fixed amount, right? But the profit, at least for that cycle, right, will depend on whether they have to pay out to you or not. Does it make sense? So here, right, this quantity, let's call it C, right, the charge amount. Okay. And so X here, the profit will really be a function of C and A, right? How is that? X will take on two values, right? Either C or C minus A. Agree? And the probability is? Yes. And so the equation becomes? Is that okay? Any question here? Okay. Okay, so I think now we move to this, but there's a variance question. So let's look at A first, right? And then we'll go back to the lecture and discuss the variance. Okay. So here, right, X would be the random variable that represent the amount win, right? And clearly X takes on values -1 and 1.1, right? With what probabilities? What's the probability that you lose? It should be 10 to the 2 and 5 squared, right? And this, you can simply say is 1 minus that. If you're pretty sure that, right, your answer here is correct. Or you if it's better to just do combinatorics here too, right? You do 10 choose 2, then you got 5 choose 2 plus 5 choose 2, right? So I think these two numbers should be equal, right? So expectation is just right, multiply that, okay? Any question? All right, so now let's take a look at variance. So before, right, we talk about variance, we want to talk about a concept called the nth moment, right? And it's very easy. The nth moment of a random variable is expectation of x to the nth, right? N here is an integer, right? 1, 2, 3, 4, right? So the second moment is x squared, expectation x squared. The fourth moment, right, is expectation x to the fourth, that kind of thing, right? And you can calculate this very easily. I mean, easily is in like if you know the distribution of x, right? The mass function of x, then you can just, you know, plug in, right, using a law of unconsciousnization. Okay. And yep, right, these are not just pure kind of like mathematical, right, intuition. Oh, sorry, mathematical calculation, right? They correspond to information about the random variables. Like the variance is about the spread, right? The third moment is about the skewness, and the fourth moment is about kurtosis, right? The fat tail, right? The tail end behavior. Now, again, right? I clarify here that they are not exactly these things, right? But if you look at the definition, so we'll look at the variance, right, which is a spread. But if you look at the definition of skewness or kurtosis, right, then you'll see that the fourth moment plays the most important role. But of course, it's not the only calculation, meaning the fourth moment is not kurtosis, right? Don't make that confusion. But to calculate the kurtosis, right, the fourth moment is involved. Okay. And you'll see that also in Math 481, for example, Edward Gersh in statistics. All right. So now it goes to variance, right? So the variance is defined as an expectation, right? So the variance is defined as expectation of this, which is, right, you should look at this as a random variable in itself. And just to make it, right, abstract, here, right, expectation of x, you can call it mu. Sorry, not abstract, make it easier to see. So this is x minus mu squared, right? And here, right, notice that with notation, things can be a bit, you can do it wrong and you read the symbols. For example, with a square like this, right? The idea is this is a square inside the expectation. Okay. Meaning that you take the random variable, you square it first before you take expectation. There's also the idea of the square outside expectation, which is this one. Okay. So you see it's written like this without the parentheses. All right. And you're supposed to know like kind of what is what as well. When sometimes like, you know, people don't put the parentheses. So the square on the random variable means that you square the random variable first before you take expectation. This, right, is just take expectation first and square. So that's just mu squared. Okay. So here, right, this is, you look at the random variable x, right? Mu is the mean of x. So basically, right, it look at the distance, right, of x away from its mean. Okay. But of course, right, the distance, so if you don't square, you have a square here, right? Then you should call it a displacement rather than distance because it can be positive or negative, right? So the square here, one of the purpose, right, is to get rid of the sign, right? So it doesn't matter if x is, right? So for example, if you have a distribution, right, where the mean is here. So it doesn't matter if it's below the mean or above the mean, right? The distance you squared is always positive. So that's why, right? It represents the spread, how far out, right, you are away from the mean, right? The spreadness on average, right? But notice, right, when we say that, then this doesn't have to be the only way to measure the spreadness. For example, this will also be another way to do that, right? Taking the absolute value only. But the difference, right, in mathematics, we call this the L2 norm. This is called the L1 norm. This is kind of not very nice, so it doesn't have as nice property as the L2 norm. So people use the L2 norm as the measurement of the spreadness. Okay. But from that point of view, right, notice that the square here is not on the same unit as x, right? So if x, for example, has unit of, let's say, I don't know, right, kilogram, then variance of x has unit of kilogram square. Okay. So you should have seen this already, right? But the true thing, or the people use is a standard deviation, right, which is the square root of the variance, right? But the standard deviation, because of the square root, also have certain not nice properties. So variance, right, end up being the quantity get used very often, and it does measure the spread, right? But do remember it's not on the same scale, right, as a random variable itself. Now, finally, right, notice there are two formulas here, right? This I would call definition. This I would call the computational formula. You can call it definition if you want, doesn't matter. But what happens, right, is that the definition kind of invokes the meaning of why the variance represents a spread of the random variable. While computational formula is what it means, right, is used to compute, right? Meaning that people don't use this formula to compute the variance. People use this, all right? And so the point is that these are equal, right? These are not equal answers, but this will be an easier calculation than that, right? This would become a more tedious calculation. So let's show, right, why these are the same. So you have expectation of x minus mu squared, right? Where mu is equal to expectation of x. Okay. So you expand the square. Notice, right, it's inside the expectation. So, right. And then you use linearity of expectation. Remember, mu is a constant. So it's like that, right? Notice there's no expectation here because, right, basically expectation of a constant is itself, right? That should be obvious. And now expectation of x, of course, is just mu, right? So that's minus 2 mu squared. So you get all right. Any question here? All right. So we'll go back to the problems, right? But now I guess it's about the right time to give you a quiz. So let's give you the problem about the insurance company. All right, this is the quiz. All right. Any question before we take a break and restart at 7:05? All right, everyone submit on time, all right? I will not accept any late quiz submission today, all right? Okay, is there any question before we continue? All right, so so basically, to calculate the variance, right, this is all we need to do for any random variable. So let's say for this random variable, for example, right, to find the variance, all you have to do is to write down x squared and things like 1 and 1.1 squared and probability, right? And again, right here, of course, is still, and actually I'm silly, right? Why do I have to write down like that? Because the point, right, is that you can use the law of the unconscious statistician, right? So variance of x is expectation of x squared minus expectation squared of x, right? Which is, right, for example, here, right, that would be, let's say, minus 1 squared, right, times whatever that is, plus, right, 1.1 squared times, right, that will be expectation of x squared, and minus, right, let's say answer in a square, for example. Right. So again, like the computation is nothing enlightening, right? It's just meant to kind of to get you to go through the routine. Okay. All right. So let's look at the properties of the variance, right? Which would help you to calculate some kind of variance more quickly. So the variance, right, of this is not a linear combination exactly, because here, right, a, b are constants. Okay. If a, b are constants, then variance of ax plus b is like that. So in particular, right, variance of x plus a constant is always variance of x, right? And the first thing, right, is if you look at the intuition of this, actually, this is very, very easy to understand, right? If you have a random variable x, right, that looks something like this, then ax plus b would kind of tend to spread x out by an a factor, rather absolute value of a, and then it got moved by b. So translation. Of course, right, the translation also gets affected by a as well. Not that the a doesn't affect the translation. So the translation, right, is going to be a mu plus b, okay, for the center, the new center. But basically, right, because these are constants, all they do is they scale the distribution and they move it, right, with some distance. But notice, right, the point is, as far as the spread is concerned, that's what the variance is, right? The movement, all right here, right? The movement does not change the spread. That's what it says here, right? If you just have a distribution and you move it exactly to the right, right, c units, then the spread of the two are exactly the same. Okay. Now, as far as the proof is concerned, right, then depends. But if you want the proof, this one probably is easier, okay, to be approached by the definition rather than this formula. This formula will be kind of ugly to prove that. But if you use that definition, right, then you got variance of x plus c, right, is expectation of, let's say, right, x plus c minus expectation of x plus c squared, like that. Okay. So notice by linearity of expectation, right, this will become right and the C cancel, leaving you with this, which is just variance of X. Right. So that's why. And so, right, here it remains to show that variance of a constant times X is A squared, right? So notice the A squared as well, and this tends to be the mistake of students new to probability and statistics. For example, when they calculate variance of 2x, they say it's 2 variance of x. That's incorrect, okay? 4. The reason is it's a square, right? And for example, variance of minus x is actually equal to variance of x. Because, right, it's square of -1 is 1. Now, how do you show this? Well, showing this, actually, the other definition is easier. The other, So, right, variance of a times x is expectation of ax squared minus, right, expectation square of ax. But notice, right, this is still a square expectation of x squared by the, right, linearity expectation. And then this, right, this is just really expectation of a times x, the whole thing squared. But, right, the a also comes out, and then comes out again as a squared. So that a squared right, so very easy, right, from that point of view. Okay. And then, of course, right, notice that the standard deviation of this is absolute value, right? Like that, right? So with standard deviation, you have the absolute value there, right? You don't have sign when you scale. Okay. Right. So same goes here, right? The variance is always non-negative. And so, for example, right, again, if someone somehow, right, writes something like this, then that's really, right, really wrong. Because, right, the variance can never be negative, okay? And so this probably is easy to know, but the variance is 0 if you have a random variable, right? And if you calculate variance is 0, then it's really not a random variable, but it's a constant, meaning that, right, it cannot be, it's not a proper random variable, okay? Why? Because intuitively, right, if something has no spread, have 0 spread, then all it does is, right, it's just really a point mass. It doesn't mean a point mass, it's just a point, right? It has no spread, so it's just a single point, right, with mass 1. So that's why, right, the variance is 0 if that's true, okay? Now, you actually, I guess you can also see it from the definition here, right? If x is different from expectation of x in any way, right, in terms of probability, then this square will contribute to the average here to make the variance positive. But anyway, right, so something that, you know, is used more in more advanced probability is the so-called Jensen's inequality that says that expectation of x squared, the square inside, is always no less than, right, or a lot of times strictly bigger than expectation of x then square, okay? And the reason is very simple, because if you subtract the two, you get the variance, and we just set the variance non-negative. So if you ever calculate this guy and it's less than this guy, then you have a mistake in your calculation. All right. Finally, right, another favorite thing is variance of sum is not the sum of the variance, all right? Expectation of sum is always a sum of expectation, doesn't matter. But variance of sum is not the sum of variance, right? It's only true if they're uncorrelated. And a more special case of uncorrelation is independent. So independent implies uncorrelation. So that's true. Also, if they're independent. But something we'll discuss is that you can have uncorrelated random variables that are not independent. So in fact, these two are not the same, right? So we just need uncorrelation, right? So in general, that's a formula for variance, right? So almost remind you of inclusion, exclusion. I mean, not in any big way. It's more like in the sense that it's not a straightforward sum, right? You have extra terms, right? And this is the covariance, right? And covariance is defined like that, right? Which is expectation of the product minus the product expectation. Okay. So that should round up the story of the variance. Any question here? All right. So let us now take a look at the next problem.
Professor,
Yeah.
what's the meaning of the covariance? Like, what's its implications?
Excellent
What?
question. Yeah, no, excellent question. So you probably, since you asked the question, you probably have heard of the term correlation, right? Correlation is covariance divided by the square root, right? Or the standard deviation, right? Like that, okay? So correlation actually is the one that often mentioned. The reason is just basically covariance got scaled, right? Or skewed, whatever, right? Got blow up by the scale of X and Y. So that's why they divide by the variance to kind of scale it down, right? So correlation is between -1 and 1, right? So now, but of course, right, a special important case or three important values, right? -1, 0, and 1, right? This is no correlation, uncorrelated is what we talked about here. And of course, right, you see because of that, that's also corresponding to covariance equal to 0, right? Covariance equal to 0 implies correlation equal to 0, if only if, right? This is perfect, right? Or positive correlation, right? And this is perfect negative correlation, right? Okay, and first of all, right, again, these days, and they assume that most of you guys have dabbled or have seen like linear regression and that kind of stuff. So right, this is so-called right Pearson correlation, right? This is called a Pearson correlation, right? It's happen what you call it, like shows up a lot there in linear regression. And the routine thing, right? People say is what? Well, right, if you are positive correlated, then if X increases, then Y increases, right? If you're perfectly negative correlated and X increases, then Y decreases, right? If you're not correlated, then there's no relationship, right? Blah, 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 right? And so sort of that's the thing, right? And that would be, and you see that covariance, then you can also tell the same story, but with a scale, right? The variance thrown in, right? So that's one way to explain covariance, right? For you. But if you dig deeper, then the story doesn't end there. Because the way the covariance and correlation here is defined, right? And there's a name for it right there, right? The Pearson correlation is quite peculiar. I think basically what it does is, right, when you have the word perfect here, right, has actually a very, very, very implicit meaning here. They somehow really measure the linear dependence between X and Y. That's why it fits nicely into the linear regression framework, right? Let me give you a very easy example, right? If you think of X and X squared, right? Or X cubed, whatever, right? Take your favorite random variables. Then it's clear that X and X squared are perfectly dependent, right? That somehow, right? Whatever that means, correct? So X and X squared are perfectly dependent somehow, right? But you could have random variable where covariance of X and X squared is equal to 0. Easy. Can have a random variable covariance of X and X squared equal to 0. Okay. How? Very easy. Why? Because you can covariance of X and X squared is expectation of x cubed minus expectation of x times expectation of x squared, right? By definition. So you just have to find a distribution where you cube it, expectation is 0, something like -1 and 1/2 each. And then expectation of itself is also 0. So this is 0. Well, you see, right, in terms of covariance and this whole nonsense, sorry, right? Nonsense is in like saying without thinking too much. If two random variables have correlation equal to 0, then they're not related. Yeah, I have x and x squared here, right? Covariance equal to 0, but they're perfectly related, correct? So that's a more nuanced, correct, aspect here that you have to dig deeper. So the story basically will continue in one direction to different types of correlation. Pearson correlation is one type. I forgot the other types of the other name correlations that try to capture different kind of dependence, right? So I'm telling you this story just to tell you that there is a standard story that people would tell you about the meaning of covariance, like that kind of blah 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 I just told you. But beware, that is not there. You can easily tear away that story, right, with examples. So meaning-wise, right, covariance is a little bit delicate, or correlation is a bit delicate to give a precise meaning to. Or if you want, the precise meaning is measures the linear dependence between x and y. So perfect correlation here tends to say that x and y have linear relationship in the positive direction. X and y have linear relationship in the negative direction. Here kind of means no linear relationship, what that means. So this tends to be iffy, so I don't really give a lot of weight here a lot. It does have a meaning in terms of variance calculation, right? Clear. But beyond that, when people want to throw that in terms of linear regression point of view, kind of have to really be a bit careful. Okay. Any other question? All right. So so this exercise, right, is to ask you to just use the rule, right, to calculate this out. All right. So I guess part of the deal here is you have to understand, right, the notation. So what should we do here in A to calculate this? What's the first step? So here, right, the square is inside expectation. So first thing to do is to expand the square, right? and then use linearity, right? So this is 4, 4. How do we calculate the last term? Is that 16? Is that the correct answer? The answer is no, right? It's not correct. Why? Because expectation of x squared here, remember, is not expectation square of x. It should be strictly greater, right? The equality only happens if it's a constant, which it is not here, right? Because the variance is positive. So the answer here is expectation of x squared, right? Routinely will be variance of x plus expectation square of x. Okay. It's 1 here. Do we understand? So this is not 16. It's okay. Any question? Well, what about B? So B is variance of 4 plus 3x, right? Is 9 variance of x, right? 3 squared, right? Which is 45. Okay. Any question here? Okay. So now we have, right? So for all the above, we have discussed basically the things that are common for all discrete random variables, right? All discrete random variables will follow this treatment, whatever they are. So now we go to more specific random variables and kind of say more specific things, right, about them. And the idea here, right, is that we'll talk about the mass function, the expectation, and the variance. All these random variables will come with parameters. So pay attention to these parameters. Basically, right, students would like to say, oh, it's a Bernoulli, it's a Poisson. That's not enough. It's a Poisson what? It's a Bernoulli what? Right? So for example, right, even though we say this because we don't want to make it more cumbersome, but a binomial would be a binomial NP. A Poisson would be a Poisson lambda, that kind of thing. All right. So there are always parameters to go with this distribution, right? That's the first thing. The second is the model, right? These are actually models, like they model situations, right? That are pretty basic, but from there, right, you can modify them for a more complex model, right? So these are routinely used to model certain things. If you don't understand what they stand for, then you would not understand why they show up in certain kind of models, right? And also understanding the modeling aspects also will explain why they have certain kind of connections, right? So we'll talk about that. And yeah, these should be memorized. Well, here I was trying to be nice. These should be memorized by students, period, right? On your exam, you need to know it, right? So you will need to know or memorize all these random variables, their expectation, their variance. There are one or two exceptions, right? I'll tell you. The only exception actually is the variance, right, of the hypergeometric. You don't have to memorize that. The rest you have to do. Okay? So let's start out with the most basic one, or the easiest one, if you will, the Bernoulli, right? So we kind of mentioned the Bernoulli in the hatch problem, right, last time. Basically, it's an indicator random variable. It takes on value 1 with probability p, right, and 0 with probability 1 minus p. So p, right, is the parameter of the Bernoulli random variable, okay? So the Bernoulli, right, have expectation p, right, because it's p times 1 plus 1 minus p times 0. The variance, right, also is easy to calculate because expectation of x squared is 1 squared times p plus 0 squared times 1 minus p, which is also p. So therefore, right, the variance is expectation of x squared minus the square of the expectation. So that's p1 minus p. Okay. And so, right, it's simple. It's so simple that you tend to miss it, but it's used in counting, right? Its most important role is used in counting a discrete count of a total of something. Okay. So, right, the next one is the binomial, which, right, so it's easier if we kind of explain. So first of all, this is the mass function, right? But it models the total number of successes in an experiment with n independent trials whose success probability for each trial is p. Okay, so the binomial, right, routinely gets associated with the coin flip. So you can do n independent coin flips, if you will, right? And probability of a head, right, is p. And so the binomial tracks the total number of heads, right, in the trials, let's say, right, or total number of successes, right? And so let's explain, right, the mass function. Well, actually, first let's explain the support, right? What values can the binomial take? Well, if you have n coin flips, right, and you track the total number of heads, then clearly, right, you can have 0 head up to n, right, heads, correct? And so the probability that it's going to be k heads, right, k in between 0 and n, is what? Well, right, this is easy enough to understand, right? K heads, the rest tails, and choose k, right, tells you where, right, the success are, right? Correct? Out of n trials, choose k to be successes, right? The rest will be failures. Okay. And so why is this a probability distribution? In other words, right, if we have something like this, probability x equals to k is n choose k, p to k, 1 minus p to n minus k from 0 to n, then why is it that sum, right, of all of these probabilities is equal to 1? What's the reason?
Is this not the binomial theorem?
Very good, exactly, right? This is this is p plus 1 minus p raised to the n. So that's exactly 1 to the n. So that's why it's 1. Very good. So let's look at the expectation, right, and the variance. So these are one of the first things you have to memorize, right? Expectation of binomial n times p, variance is n times p1 minus p. All right, so now, right, let's verify this formulas. Oops. Whatever. Right. So expectation of x, right, will be sum k, probably x equals to k, right? K from 0 to n, which will be sum from 0 to n, k, and choose k, p to the k. All right. Now look at this, beautiful sum, right? And explain to me how it will simplify to n times p. How does that work? And for one thing, right, I hope you see this is the reason why you want to, or you need to memorize the expectation and the variance of common random variables. Because, right, you're not going to sit around and figure out this kind of expression and know it's n times p, right? I mean, well, you can, but it will take time and, it's not efficient. But we still, right, want to explain the calculation at least once, right? So the way you do it is, right, look at the binomial coefficient or the combinatorics, right? That's n factorial over, right, k factorial, n minus k factorial. And this k and k factorial, right, seems very attractive to cancel, except that, k equal to 0, right, would make an awkward cancellation. But notice that k equal to 0, right, doesn't really contribute to the sum anyway. So we can move that to k equals to 1, right? Okay. Now, once we do that, then we can have n factorial, right? K minus 1 factorial, and then n minus k factorial. But notice, right, because it's k minus 1 now, things seems to want to go down one notch. So we want to turn this into an n minus 1, right, to match the k minus 1. So n minus 1 factorial, right? K minus 1 factorial. Notice the thing inside will become n minus 1 minus k minus 1, right? So this match perfectly. Of course, right, what costs us is an n outside, right? Because n times n minus 1 factorial is n factorial. And p to k, we will change it to p to k minus 1, right? To match the k minus 1. And 1 minus p, we have n minus 1 minus k minus 1, so no need to change that. Of course, that will cost us a p outside. Notice that's that n times p. Okay. Now, so what's inside the expression here? Well, fair guess, right? It must be 1. But why would that be so?
It's another binomial.
Right, but you want to, first of all, change it to something like this, right? So basically, you move it from 1 to 0, right? And you basically, this is called a change of index, so that this k minus 1 becomes a k, right? Now it becomes a binomial. N minus 1 choose k, right? Now this is a binomial. So that's n times. Okay. Like that. Any question? All right, so what I have done here, right, is called the analytical proof, right, of the description, meaning that, right, you just do everything analytically, right? You do combinatorics to simplify, which is legit. But this is not the road that the probability people tend to take, or this is not a probabilistic approach. Because, right, notice that, okay, this is fine and good, but what about the variance? The variance, you see, will require you to compute expectation of x squared, which will involve, right, dealing with this expression k squared. All right. So notice that we just did a k cancellation with k factorial, right, to get to k minus 1 factorial. K squared, you can do it, right? But you can at least see that is not fun, right? It'll be quite tedious. All right, so what's a better way, or what's the probabilistic approach here? The probabilistic approach, right, as hinted above, is to note the relationship between a Bernoulli and a binomial, right? This is exactly what I mean about what I talked about when I say connection between random variables. So a Bernoulli is a sum of a binomial is a sum of independent Bernoullis. Of course, a Bernoulli, right, is a special case of a binomial, right? Binomial with one trial. That's trivial, right? The one that we are interested in is a binomial is a sum of independent Bernoullis. Why? It's there by the very definition, right, of what these random variables do, right? Bernoulli is like the result of a trial. Binomials is a total number of successes in n trials. So clearly, if you sum the individual trials up and you make sure that they're independent, then you get a total number of successes, right? Why would this be useful? Again, right, because then expectation of x will be the expectation of the sum, which is the sum of the expectation by, right, linearity of expectation. But each of them is a Bernoulli, right? And Bernoulli has expectation p. Where was it? Right here. Therefore, right? It's just n times p. See? 5, 6 lines of analytical calculation, right? Reduced to a single, easy probabilistic argument. Of course, you know where to look, right? What about variance? Variance of the sum is not usually the sum of the variances, but here we have independent. So we can pass the sum inside, the variance inside. And again, they're Bernoulli. So their variance is P1 minus P. So is NP1 minus P. Like that. Any question? So let's take a look at this. Right. All right. So why does this problem and the next problem fall under this group, right, of identifying the random variable? The reason is, right, if you don't recognize, right, what model is being used, and not that, right, that there has to be any model here. For example, right, the ones that we looked at above, these ones, right, they don't follow any kind of model, or what I mean is they don't follow any well-known distribution. Okay. And if they don't, that's fine, right? All you can do is to write down the expression like that, right? Nothing much you can do. But if they do follow well-known model, then A, right, if you do calculation by definition, that's a waste of time, waste of your time. And second, right, your answer, if you give the answer in the abstract like this, right, remember, right, in this class, this is acceptable. It's not even acceptable, right? This is accepted because unless you somehow have access to calculator, which is forbidden, right, on the exam, I doubt anyone can, right, figure out these things or care to figure out these things. Okay. So, however, this is not acceptable, this kind of expression, this kind of answers, in this problem. The reason is the problem here will belong to a class of random variables that's well recognized. So the answers there is much more simplified. Do we understand? All right. So for example, right, what's the answer to part A? If X is the number of answers, right, correct by both A and B, then what do we observe about X? X is a binomial, right? 10 and what? What's the success probability? Point 0.7 times 0.4, right? And so that expectation of X will be That's it. Any question? So B, right? It's just for the variance, but notice that it's not the variance of the same random variables, right? It's by either A or B. So we need to kind of give another random variable, right? Then what distribution does Y follow? It's also binomial, right? And 10, well, what success probability?
Uh, 0.7 plus 0.4 minus their intersection.
Right, which is what?
0.28.
Correct. Okay, good. So the variance of Y will be 10, right? Whatever that is, called P. Okay. All right, any question? All right, so I think let's introduce the next random variable, and then we'll kind of go talk about it in more details next time. The next one, let's skip the multinomial. The next one is a hypergeometric. Okay. And let's just talk about the model. The model of the hypergeometric, right, is to, and the thing about the hypergeometric is it has a lot of parameters, 3 of them, right? But it's not that scary. You understand what it is, right? Well, you kind of see the point when you understand the model. So you have an urn, right, consisting of n balls total. K of them is blue, and then the remaining, right, is another color. Let's say red. Okay. And then you select a sample without replacement of size n, right? And among your sample, you want to count how many blues, right? How many group of this type in your sample, okay? That's what the hypergeometric tracks. But here, let's just make a very simple observation. Let's suppose that it's not without replacement. Let's say if I do it with replacement, right? Just for whatever reason, I want to do that. Then with the same setup, what random variable will I have? If I also sample, right, size n, and then I want to track how many blues I have in my sample. Same setup, but now the only thing changes with replacement. Then what will I have? So note, right? If you do it without replacement, then the balls, right? The color of the balls are not independent. But you do it with replacement, then the colors of the balls, right? The results of each ball is independent. So you think about it, but basically, if you do it with replacement, then this will be a same thing, but it'll be a binomial, n k over n. All right. So a hypergeometric actually is the cousin of the binomial. It's basically the binomial, but when the trials are not independent, right? Of course, the trials are dependent in a specific way, but that's why the hypergeometric is always there, because it's sort of like the if binomial, right, in this context will represent sampling with replacement, then the hypergeometric will be the same count, same experiment, but now without replacement. All right. And that would explain, for example, why the expectation of the hypergeometric is the same as expectation of a binomial. All right. But we'll look at that later. Okay. Any question? All right. So if not, let us continue on Monday.